yes.
But that effect is the soul of the Aronoff-Bohm effect, which surprised the world in the late 50s because it was discovered so late into the game.
It is a same sort of thing, that's right. Well, of course, like so many things, people point out that this Oscar Reuterswärd, who's a Swedish artist, had drawn things like this before.
Uh-huh.
I think round about the year I was born, he had a picture, which is all with cubes going around. It wasn't exactly the same, but it was.
Well, I think I've seen these floating.
Yes, the one with the cubes. Yes, and then he had versions with staircases too. He never put any perspective in it, which seemed to me that was something
missed opportunity.
Yes. No, in my triangle, I did put some perspective.
Yeah.
So that slightly, you can see, but you can do it with a perspective, and it still works.
So what I want to get at is, I think also that we have this very funny thing that happened recently, starting from the early 70s, where we started mistelling our own physics history because of the needs of the community to look like we were succeeding when we weren't, or we were succeeding at something different than we were trying to succeed at. And in part, one of the reasons that I want to use this podcast to discuss science is to give alternate versions of what's happened. Mm. And I want to explore one or two of them with you. Now, you and I have a very funny relationship, which we don't really know each other. But you were quite close to Michael Atiyah at various points. Yeah. And I was...
Well, we were graduate students together in the same group.
In the same year.
Absolutely, right? Same year, yes, with the same supervisor.
Incredible.
Yes, that's right.
And then you continue to cross-pollinate ideas through the years.
Yes, absolutely.
Now, for listeners who don't know, Michael Atiyah was one of the absolutely most dominant and generative, I don't even know what to call him, like beyond genius, a seer of type.
Well, he had such a broad understanding of mathematics. It's partly
and geometry more generally, and analysis. I mean, just incredible. Yeah. And algebra. I mean, he wrote a book on commutative algebra. Now he had a partner for much of his career, Isidore Singer, who I was quite close to for a period of time.
Sure. Yeah.
And was, again, another one of these figures that if I'd never met one, I wouldn't know that the human mind was capable of that level of repeated insight.
Yeah.
And they came up with something called the Atiyah-Singer index theorem, which governs worlds in which there are no time dimensions, but only space dimensions, or no space dimensions and only time dimensions. But there's no...
just equations without any differential equations.
Well, differential equation, if you think about differential equations as coming very often in three main fields of study, elliptic, hyperbolic, and parabolic, then the idea is that wave equations would be hyperbolic, the type that you're worried about in physics, but things like soap films look like elliptic equations. And Atiyah and Singer had this incredible insight into the nature of elliptic equations. Do you... Go ahead.
Sorry, no, I was going to say it's an extremely general theorem which goes over all sorts of different areas of mathematics and it has applications.
Well, it sort of tells you that the knottedness of some beautiful space that you might be exploring, like some kind of high-dimensional donut that's knotted many times around itself, whatever you want, that topological knottedness tells you something about the kinds of waves that can dance on that space.
Yeah. No, it's a very remarkable theorem, certainly. Yes.
Does that theorem in the so-called elliptic category, world of space and no time, let's say, relate strongly, in your estimation, to the most important hyperbolic equations that govern the waves that make up our physical world due to the constraints of relativity in a world with one time and three spatial dimensions?
Well, all I can say, if I use the theorem on at least two different contexts, yes, maybe more. So, I'm not an expert in that area at all. And it was mainly when I was trying to solve a particular problem. I don't know how much detail you want to go into these things. It had to do with how to make twistor theory work in curved spaces. But I ran up into a question which has to do with complex geometry. So you've got geometry in which instead of using real numbers to use, you think of measuring with rulers, say, and the ruler is one-dimensional. The numbers go along one dimension, if you like. And complex numbers, where you have the square root of -1 incorporated into the number system, they're really two-dimensional. So the geometry of complex numbers has twice as many as the real numbers. But the geometry of complex numbers is particularly fascinating. Or that's the algebra, you might say the analysis or whatever it is. It's particularly fascinating. And I was sort of, when I learned about this when I was at an undergraduate doing mathematics, and I thought it was incredibly beautiful. Because when you talk about real numbers, you have, you can have draw a curve, which is a function. So this curve has some shape. And you might want to see, is it a smooth curve? That means you have a tangent direction as you go around it. Maybe it jumps, so it's not even continuous. Or maybe smooth, or it may be you have to have a curvature of this curve, and you might not be smooth enough to have curvature. So there's 1 degree of smoothness, or 2 degrees, or you can have 3 degrees or 4 degrees, and they're all different, or an infinite number of degrees, or that you can expand your function in the power series. They're all different. And then when you learn about complex, you say, oh, we now do it all over again, and you've got your analysis, or algebra, if you like, or geometry, where it uses complex numbers. And then suddenly you find that if it's smooth, everything comes with it. You can differentiate as many times as you like. You can expand as a power series. And I thought that's incredibly magic. You just have to do it once. Rather than there's all these different kinds
I should say that mathematicians
yes.
quite often view the complex case, the case of complex numbers, as the natural case,
yes.
and the case of real numbers as artificially tortured.
Yes,
which is a complete reversal from how most engineers and physicists. Yes. And you actually have been quite instrumental in making the case for the fundamentally complex nature, that it's not just a convenience that we use complex numbers in physics, but that nature appears to be essentially complex.
I think, you see, by just hearing this nature of complex analysis,
right,
and how beautiful it struck me as being, and I had this sort of feeling, wouldn't it be wonderful if these numbers were somehow the basis of way physical world operates? I have no reason to think that. And then I learned about quantum mechanics, and I was amazed to find, there they are. They're not just useful convenience. You can use them to simplify ideas in mathematics. You can, might have an integral.
You would have to work awfully hard to get rid of them.
Yes, but there are things you find, a little trick to do it. Out these formulae come with contour integrals, and they drop out in an amazing way. And I thought, well, that's a piece of magic, but it doesn't tell you anything about the world. It just tells you this is a neat way of doing things. And then I learned about quantum mechanics, and suddenly these numbers are right there at the basis of the whole subject. And I thought that was an amazing thing. Maybe these complex numbers are really there at the root of everything.
I mean, I think you wanted to talk about twistors.
Well, that was
yes. And maybe I can intro that and then try to fit that into this history that I'm claiming we don't tell. Now, one of the ways of describing what twistor theory is, and of course it's a bit of a tall order for a podcast, is that you are replacing Einstein's space-time with a larger structure that in some sense implies space-time. But where you can take all the data that roams around on space-time, the waves, the force, the matter, what have you, and you can, as mathematicians might say, pull it upstairs to this larger twistor space where you might have a couple of extra tricks up your sleeve because the extra space that you've created to augment space-time with has this kind of complex number aspect baked into it.
Yes, well, it was something. Just to go back for a moment, it was to explain the Atiyah-Singer theorem. That's why it was useful. I'll come to that in a minute because it's a very interesting story. The way these things sort of come together and take many, many years sometimes before they come together. But I was really intrigued by these complex numbers. And there is Well, let me tell you what's sort of the origin of the twistor idea. I was struck by the fact that, you see, people know that when things travel with a great speed, and according to Einstein special relativity, they get sort of flattened in the direction of motion. Now, this is a way of talking about it, and you get this Lorentz contraction, as it's called. Now, I was playing around with relativity and thinking about, it was this two-component spinners, and thinking about how the geometry of it worked. And I realized if you think of the sky, you see, the sky is where you have vectors in 4 dimensions. Think of a vector as something which has a magnitude and a direction to it as well. And in ordinary 3 space, you've got this idea of a vector, which is quite common, people know about. But when you're in 4 dimensions, then you have space and time together. But you have particular vectors which are called null. And these are the ones along the light cone. So this is, see, an ordinary vector might represent a velocity. So you have a particle moving along with a certain speed, and your 4-dimensional vector would point along the velocity or the momentum of that particle.
So now, weirdly, in the space-time metric of Einstein,
yeah,
these are vectors that are not zero, but if you used Einstein's special rulers and protractors, what would the length of these vectors
well, the vector
be?
is they're zero.
They would,
exactly
so it's a really... It's linguistically tricky to talk about these things because they're non-zero things that would be measured to be of zero length if that concept of length was in fact extended from your normal concept of length.
Yes, the idea that something of length 0 means it's 2 points, the distance between them is 0, you think of them right on top of each other. Or if the distance is very, very small, they're pretty close to each other. But in the kind of geometry, we'll call it Minkowski geometry, because although it's describing Einstein's special relativity, the geometry was not Einstein. People often say, oh, well, Einstein introduced 4-dimensional space-time. That's not true. It was Minkowski. And Einstein...
I said that this is real. This is not just a sort of a weird artifact of the description of various processes that were being entertained.
Yes, but it's a kind of geometry. And Minkowski showed that the space of special relativity is really 4-dimensional, and it's this kind of geometry in which you can have distances which are 0, although the points are a sort of long way away from each other. And this represents a light ray. So you have one event, say, and then the light through that event reaches another event. When I say event, I mean not just a spatial position, but the time as well. So
you mean a position in space-time? In
space-time. Yeah. So you need 4 coordinates, 3 space and 1 time coordinate. So that's what we call an event. And so you have a point or an event in space-time, and imagine a particle moving with the speed of light to another such event. Now the distance between those two in this kind of geometry that Minkowski introduced is 0. So, and Minkowski played around with different kinds of geometry, and he realized that special relativity is really best described by this kind of what we call Minkowskian geometry. So you can have 0 distances, and yet the points are not on top of each other.
So your idea was to take all the points that are bizarrely 0 distance away and then make those the new points in a new space?
Well, it wasn't quite that. I had to come up to this slowly because it took years. But the initial idea isn't so hard to understand, really. You see, if you look out at the sky, what do you see? Well, you're seeing light rays, or you're seeing photons coming to your eye, which have traveled with the speed of light. So the world line in 4 dimensions of that photon is tilted over at what represents the speed of light. Now, in this Minkowski geometry, that distance, well, it has a clear meaning. So let me give that. Suppose the photon is emitted at one point, one event, and received at another event. Now, to that photon, the time between one and the other is 0. And that time measure is exactly the distance measure in Minkowski geometry. Suppose the particle was not traveling with the speed of light. Suppose it traveled with half the speed of light or some other speed. Then its experience of time is exactly the distance according to Minkowski's geometry. So you say, if it travels with a very, very, very great speed, suppose you travel to a planet which is 4 light years away, and you travel with, I won't do the calculation right here, but with half the speed of light, then the experience of time you experience is less than the time that somebody here on Earth would think that it took you to get there. So as you travel faster, your experience of the passage of time slows down in a sense. You don't think it's as long. And if you actually travel with the speed of light, that experience would be 0. So this is the experience of the length of time. If you you could have a very, very good clock you carry with you, and you see how that
clock made of pure light. It all gets pretty heady out here.
Well, you don't make it out of. You can imagine a clock, say a nuclear clock or something, and you're not traveling with the speed of light because you can't get to the speed of light.
Well, that's what. Okay.
But the time measured by that nuclear clock would be the distance in Minkowski geometry.
I should point out, just for our listeners, that even people who do this field of differential geometry morning, noon, and night in math departments almost never choose to work in worlds with some temporal and some spatial dimension.
Yes,
because it breaks your head.
It's a very different intuition.
Very different intuition.
And when you go back and you think about the puzzles that people had when Einstein introduced his special and then most particularly general relativity, they found it very puzzling. You could look at the arguments people had.
Well, we keep using these words like time and length and all of these things that have become, we don't recognize that in that one innocent decision to break off one degree of freedom and treat it differently.
That's right.
That all of our linguistic intuition goes out the window.
You have to start all over again.
Yeah.
Well, it was a curious experience I had because I was giving a series of lectures in Seattle. These were the Battelle lectures given in, what was it, I forget exactly what the dates were. Maybe it's around about 1970 or something like that. And there was a collection of mathematicians and a collection of physicists. John Wheeler and Cecile DeWitt had organized this. It was a very interesting meeting where people from both areas of expertise were brought together. And at that time, it's hard to believe now, but at that time, mathematicians and physicists were barely talking to each other. And they got me to give us a series of lectures. And
this is before Jim Simons and Cian Yang get together in Stony Brook?
There's a good question. When was that?
That was 75, 76.
It was before that.
Okay, wow.
Yes,
Okay.
it must have been before that. Is that right? I think so, yes. I really have to. My memory of dates is not.
Well,
very clear.
if you'll, I know you're hot on the trail of this, but just to leaven something in, Roman Jakiv at MIT once beautifully said, and I don't think he wrote it down. He said, we didn't understand the partnership that was possible between mathematics and physics because we, the physicists, used to talk to the analysts. And he said the analysts either told us things that were absolutely trivial and irrelevant or things that we already understood.
Yes.
He said when we talked to the geometers, we started to learn new things that we'd never considered.
Yes, well, there was very much cross-fertilization there. But I was going to say, I gave these lectures, I think it was 12 lectures, and I wasted my time on something I won't go into, until I left myself only 3 lectures to describe the singularities, the black hole idea, which wasn't, the term black hole wasn't used just then, but the collapse.
It was just called the Schwarzschild singularity?
Yes, well, it was called the singularity when that was the thing. People called it the Schwarzschild singularity. It's what we now call a horizon.
Right.
And I remember on my, the third lecture from the end, describing basically what we call a black hole. I was talking about the Schwarzschild singularity. And I was explaining that it was basically to do with the zero length business. And Steenrod was a very distinguished mathematician.
From Princeton, Norman Steenrod.
And he'd written this book on fiber bundles, which is absolutely...
impenetrable.
well, impenetrable, but also fundamental to the subject.
Yes, but it's so impenetrable that I never got to the point of it being fundamental.
But anyway, he was there at the back of the room, and I remember telling him about this, and he was absolutely dumbfounded. Now, you see, here's somebody who's a real expert at this kind of geometry, Riemannian geometry, or whatever you call it, where you have the notion of when the distances are small, then the points are close together. And here you have this other kind of geometry, and the intuition you need for that geometry was completely foreign. That's the point you were just making.
Well, because we do have this weird way of talking about something that sounds like this. We might call it like non-Hausdorff topology, but it is a Hausdorff topology.
Yes, this is.
But so the problem is it's pulling apart two different notions of the word close.
That's right. Exactly. That's right. Because you think of close means a small distance.
Right.
So you imagine a little tiny ball where the distance from that point is small.
Mathematics makes you pay for every attempt to sort of intuitively encode something that isn't precise.